Hello, everyone. Today I'm going to give a talk about the ReduNet network, deep convolution networks from the principle of rate reduction. My name is Ima from UC Berkeley, ECS department. So today, because the talk is only 30 minutes, I have a full version of the talk, which is 1 hour long, English and Chinese on the web, in case that you need to know more details about today's presentation. And, in the past 10 years or so, we have been fascinated by a tremendous advance in deep learning, right? That's brought tremendous technological advances. And, but yet, at the theoretical level, many phenomena brought by deep networks and deep learning has been a mystery to us, right? So, and this work is to attempt to give a sort of a plausible theoretical framework that we are able to interpret or understand what deep network is trying to do. What is the objective of deep networks? And also from that objective, we'll see that can we actually derive the architectures, the structures, and the operators of deep networks from very first principle, right? Principled approach. And really understand deep networks as a full white box instead of a black box. And this opens up many open problems and theoretical, algorithmical, and also applications, and as we'll see. So about 10, 12 years ago, deep networks really trying to study the high-dimensional data classification problems, right? So imagine you have multiple classes of images, and they sit on very high-dimensional spaces, millions of pixels, right? But each class of objects may be sitting on a no-dimensional manifold. And deep networks is trying to try to learn a mapping from those data, multi-model data, directly to one-hot class labels, right? So, and this is a very complicated function, can be modeled by multi-layer networks. This has actually seen very tremendous success, and in some things is really what's driving the success or popularity of deep network is precisely that it lumps a lot of issues into this black box, right? Make the practice of deep learning simple and easy. But that maybe make the practice easy, but actually make the understanding hard, right? Once you have a lot of those components mapped into grouped into a black box, right? So one thing, how to learn this mapping, right? It's very straightforward, right? You really want the output of this function f of x really match the best with the desired label of the input image. And this cross entropy is one of the most popular object function people use to train the neural networks. But so despite all this, empirical success, I mean, there's actually quite a few elephants in the room, right? For example, from classical theoretical understanding, we know if we choose a network large enough, we actually can fit arbitrary input-output relationships, right? Including, you can even arbitrarily change the output labels and also even scramble the pixels. And yet the network still can fit the training data perfectly. Hence, once you fit the training data perfectly, you really ask yourself the question, then what the network have learned, right? Intrinsically and within the network, statistically, geometrically, what the features have been learned inside the network is really not very clear. And also, despite the tremendous empirical success, but many of the highly engineered networks actually do not have guaranteed properties, desired properties, such as we want the classification to be robust to attacks and so on, or even to be the detection to be entirely, truly invariant to the locational object. Actually, yet to this day, there's still no theoretical guarantee for any of the networks. So in this work, we're trying to shift the study a little bit back a little bit, right? Instead of trying to, train a network to fit input-output relationship, we really try to understand what really the network, deep learning, is really trying to learn about the data. So here, I mean, the question is that if our data, we assume our data lies on no-dimensional submanifolds, right? And we try to learn a mapping, and try to make the representation of the data easy to use. We can actually make it our sort of wish list, right? So we can using the network to memorize the data, right? But hence the network is much more compact than the raw data. Hence, it's sort of like a parametric model. And also, but the original data could be nonlinear, distributed in the original space. And also to make the use easier, right? We wanted to interpolate or extrapolate data. We wanted the representation, at least for each class, to be linear, right? Finally, for purpose such as the classification, we also wanted the representation to be highly discriminative, meaning that the representation, let's say the different linear subspace of representing different classes, will be highly incoherent to each other, right? So this actually constituted as how sort of desired wish list. But how do we make this precise mathematically, right? And what did the deep network play a role here? So this actually brought us to the sort of goal of what really the representation. What is a good representation, at least in the setting of classification, right? So here is the three objectives. They're very natural, right? Meaning that if for the images within is the same class, we want the data, the representation, to be highly low-dimensional, right? They stay close together, and also they're low-dimensional linear subspace. And between classes, if images or sample belong different classes, we want the representation to be highly incoherent, right? Finally, we also want the representation for each class to be as diverse, as rich as possible, right? Why is that? Right? Because for example, we want to classify apple from oranges, right? We want to know all information, all characteristic about apple that differentiate apple from oranges or other classes of objects. We don't just want the color, right? We also want the shape, the shape of the leaves, and so on, so the texture, and so on, so forth, right? Let alone some, computers are also called apples, right? So the very popular cross entropy objective we saw earlier actually do not have this property, right? Because there's actually recent work from Dollars Group showing that if you train a neural network with the cross entropy, you end up with the features eventually collapse to one-dimensional. Now, how do we measure the goodness? Those are my wish list, right? The desired property of what we call the linear discriminative representation. But how do we actually set a mathematically quantitative goal to achieve this? Then if we are allowed to map our original data to some nonlinear features, right? So there's information theoretical quantity we can measure. For example, if all the features, what is the volume spanned by all the features? Right? This is actually given by this a very intrinsic measure we call the rate distortion, meaning that if I wanted to encode my data, those matrix, subject to some quantization error, epsilon, right? And this expression gives us the number of binary bits in order to save the data, a Z matrix, in the computer. So this is actually from information theoretical. In a geometric sense, you can think about this actually really measures the volume of the space spanned by all the features with epsilon ball packed into how many epsilons of ball can be packed into the volume of the space. Now imagine your data also have multiple class, right? Has some intrinsic structure, low-dimensional intrinsic structure. You really don't need all the blue balls, right? You only need those green balls to pack around the data. So therefore, if you're able to partition your data in a very judicious way, right? And then the average number of volume actually given by this average of those K classes, right? And don't be scared by this expression. This expression is exactly the same as this, only that apply that formula to the individual classes. Data belongs to different classes. The pi is just the membership, right? The point I, the sample I belongs to class J. So basically, this is the average volume or average number of bits for all the K classes if you partition the data into K. Hence, the very natural objective, right, is that in order to group similar things together, push different things apart, we really wanted to maximize the difference between the space of all the features and the volume or space for individual classes. Right, it's very, very simple philosophically, right? Just all the features should expand as large as possible because we want the different classes different, and we want to compress all the features belongs to the same class as small as possible, right? It's really the similarity contracts and dissimilarity contrasts. Intuitively, this quantity looks a little bit complicated, but actually later on we will see that the whole deep networks come from this. Interesting, there's something very magical about this expression. Although it looks complicated, but geometrically it's very, very intuitive, right? So we really want to say the first term says, if I consider all the data union together, what is the entire space, the span? How many sphere, epsilon ball, I can pack into a sphere? into the space. And the second term are precisely if my data lies on the two lines or two low-dimensional subspaces, I only need those green balls, right? The number of green balls in order to pack the data. Therefore, the delta R, we call the rate reduction, is precisely the number of blue balls, the space in between gets counted by the epsilon ball, right? So therefore, this actually, in order to obviously see, we actually prefer, right? Intrinsically, you can see the data in both left and right, the data lies on two lines. But we actually kind of prefer the configuration on the left. Why? Because it's more discriminative, right? Therefore, in order to find if I'm allowed to map my data, right, into a feature space, I want the difference of the whole and with the parts as large as possible, right? This really we call the maximize the coding rate reduction, the space of the blue balls, right? And once you realize that this is something you desire, right, you realize that in order to compare left and right correctly or fairly, you need the scale of the ellipsoid and also the sphere at the same scale. Hence, you need to normalize the feature, the size or scale of features, right? Hence, in the literature, there's a lot of work about normalization and so on. Finally, that although this objective looks very intuitive, it's like as simple as bin counting, right? But does this actually serve the purpose? Remember that the wish list, what we want our representation to be preferred, right? So it turns out that actually under fairly broad conditions, right? If you're able to maximize the rate reduction, then the resulting final optimal configuration of your feature precisely satisfies the conditions we listed earlier, right? Different the data belongs to different class will be a low-dimensional subspace. And also those subspaces for different classes will be exactly orthogonal to each other. In addition, even the distribution of the feature within each subspace will be as very diverse. Actually, there will be almost isotropical, right? Hence, this is a sort of like generalized the slogan from Aristotle, right? The whole is greater than the sum of the parts. But for good representation, the whole is maximally greater than the sum of the parts. Right, this actually has a flavor, that people have been playing with expansion, contraction, and so on and so forth. So you have heard about the contrastive learning, contractive learning, and actually this is very much gets unified into this single principle. One thing that one you can do is that you can actually train using this objective to train your neural networks, right? And instead of have to to test how good your neural network in terms of accuracy of classification, here actually you can look at how good your neural networks by monitoring 3 geometrically and statistically meaningful quantities, right? How the total coding rate expand, how the individual classes gets compressed, and how their difference grows, and so on. And contrasted to cross entropy, right? This is on the CFAT10 datasets and the realistic datasets. And everything else is the same. The same data, the same networks. The only difference is the objective function. We replace cross entropy with the rate reduction. And here you can see that the resulting features, right, are highly orthogonal. It's very pretty, very, very clean, right? Yet the final feature learned by cross entropy actually has a lot of crosstalks. Also, for each class, right, and the rate reduction encourages diversity, richness in the features. You can see the PCA of each class is actually quite evenly spread. Those subspaces actually all highly meaningful, right? You can here we plotted out the axis of those for the bird. There's a 10-dimensional subspace, right? We plotted out those principal components within each subspace and plotted out the images that align with each of those principal components. You can see that those coordinates of the image gets embedded into those subspaces, highly meaningful and semantical. And in addition to that, right? So remember that we are no longer fitting the labels. Every single label given to me, just in case the label is 10%, 20%, or 50% of the labels are arbitrarily corrupted, right? So the fitting using cross entropy to fit every label is not a very good idea. The rate reduction is trying to learn what's in common, fit one subspace to all the data belongs to the same class. So it's actually, we'll only compress what can be compressed. We'll ignore all the mislabeled data. Hence, you can see that the feature learned from MCR is highly robust to actually the corruption of the labels. Now the question is, are we actually happy about this, right? Satisfied? Yes, maybe it's a little bit, right? So the object function becomes more intrinsic, more interpretable, and also even the features we learn, right, are on subspaces and so on. They're also more interpretable. And also we saw that they're also very more robust to corruptions in labels, right? For those things that we're very happy. However, how to model this mapping from the original data to the feature space? We still borrow deep networks, right? ReduNet in this case, and still black box task, right? Why do we actually need a deep network structure? And what are the roles of linear and nonlinear operators in the system? Right? In particularly, we use convolutional neural networks, but to this day, nobody understands why we need a multi-channel convolution. Right? The question next is that can we actually convert this to a white box? And the good thing about have a very clear objective is that we can directly optimize this. Right? This is a very sophisticated nonlinear non-convex object function. However, let's conduct a very simple strategy to optimize it. Right? And suppose we just optimize this object function using projected gradient descent. Right, compute the gradient and do the iteration, and of course everything needs to be normalized. Now once you do the computing the gradient of the object function, something magical happens. You actually notice that the gradient has highly structured, right? It looks like some matrix hitting the data, and also a multiple linear operator operating on different pieces of the data. The C applies to each class, right? The gradient actually has this form: an expansion term, a compression term. And those terms, those matrices has this very peculiar form, right? If anyone familiar with statistics, recognize they are precisely E multiply any vector are precisely the residual of that vector against all the data belongs to the same class, right? It's actually from this ridge regression, residual of the ridge regression. Hence, if you want to expand your data, you maximize the residual. Or if you want to compress the data in different classes, you reduce the residual. Right, that's what the gradient flow is really doing. Schematically, this is very, very intuitive, very, very simple, right? So remember, our goal is to try to push our data into orthogonal subspaces, right? Of course, we don't know how to do that globally, but locally, we actually can compute the gradient flow, right? So to push the data locally along those gradient flow, eventually they will converge on the orthogonal subspaces. And this is one thing that remember, this is piecewise linear mapping, and for the pieces associated with each class, we need to know the group numbers, the group membership. But that is only given for the training data. What about the data not in the training? Well, very simple. We know CZ is residual to each class. Hence, this already allows to build a classifier. Right? I mean, use a softmax, whatever your favorite choice. In fact, if all your features are in the first quadrant or positive, this can be approximated by a ReduNet network. Hence, choice of the nonlinear operator, you know what the essence is actually try to approximate this gradient. Right? There's lots of mystery about it. So once we do this, once we conduct this gradient descent, right, for my features, iteration by iteration, if we draw out the diagram from one iteration to the next, you can see that we, from the features in the previous iteration, we pass through linear operators plus identity and sorted them, gate them through a classifier, and then aggregate them together and then normalize them, send to the next layer. Right? So you look at this optimization procedure, precisely resemble what people have found empirically, the residual networks, right? But there's a big difference, right? And later on, actually, residual network people find out that if you have a parallel groups, the performance is better, right? That's precisely resemble the meta structure derived from the rate reduction. And yet, there's something magical about this, right? Because the whole network is constructed in a forward fashion instead of back propagation. And even the largest network, right, let's say is the 1.7 trillion switch transformer, resemble exactly the same data structure. Does this work? Yes. You can see that this is the input data. Really, that the network already try to push. This is the initial configuration. We'll actually squeeze each class and push all the different classes to the orthogonal subspaces. In reality, in practice, we also care about the classifying data that has highly geometric structure. For example, images are rotated or translated should belong to a same equivalent class, right? And till this day, all the highly trained neural networks actually are not actually fully invariant, right? The traditional way is just to augment your data, train the network. Now the question is, in our setting, this can be stated very, very cleanly, right? We actually just wanted to map all the translated or rotated image into the same subspace. How do we do that, right? Then we just concatenate all the data translated into the same matrix and compress them together. As soon as you do that, you realize something magical happened, right? As long as you actually compress all the transformed images or text together, the gradient operator, remember those E channels, C channels, right, operator, automatically become convolution. This is very different from we choose convolution to achieve equivalence. Here, not only the task of compression stipulates you need to use convolution, but also tells you what the convolutions are, those values of the operator. You can also generalize this to multi-channel signals, right? For the interest of time, I'll ignore the detail. But really, if you have multi-channel signals, you try to compress all the multi-channel translated or transformed multi-channel signals all together. The operator, the gradient descent operation, automatically become multi-channel convolution. Right? This is probably the first time, right? Multi-channel convolution gets justified, why you need to conduct multi-channel convolution. However, computing those operators is not a picnic, right? This is a humongous matrix that you need to do inverse on. Right? C is the number of channels, N is the number of pixels or number of dimensions of the signal, right? This is humongous to invert, but actually this is not that hard. Turns out this matrix is highly structured, right? We know that it's a block circulant matrix. Hence, the circular matrix can be diagonalized in the frequency domain. Therefore, computing this operator, this gradient descent operator, in the frequency domain, the complexity is dropped from cubic to linear. Right? This is also, again, the first time, right? We actually formally proved that convolution neural networks is much easier, much more economic to learn, to construct in the frequency domain. And in nature, our visual cortex compute in the frequency domain. And for the first time, we are able to write down a deep network or every single operator, every single parameter as a black box, as a white box, right? Actually, in the spectral domain for saving the computation. And also now, this is a sort of an interesting thing, right? So for the first time, we start to see the elephant in the room, right? So that if your task is to try to map multi-class signals into orthogonal incoherent subspace, then everything that you saw in the modern neural networks become a necessary component. They're not that you choose, you try the work. It's actually mathematically necessary. Sparse coding really allows you to separate different classes. A deep network is just to maximize the rate reduction, right? To get the configuration better in an incremental way. Spectral computing is necessary if you really want to save the computation from cubic to linear. Convolution, multi-channel convolution, normalization, and linearity, they arise as necessary components. You don't get to choose them. Okay, you don't get to even try them. And does this work? Yes, it actually works very, very well. For the first time, you actually be able to construct the convolution neural networks, right? However deep you want, right? Because every layer is just iteration of optimization. And by the end of the day, the feature you learned are going to be completely orthogonal to each other. In fact, this is for features for all rotated instances, not just the augmented like 10, 20. This is on all orientations. 10 classes is the same picture, and also the same story for the translation. If you have now we don't consider this translated on 5, 10 augmented translation. No, this is on the entire torus. Every single pixel you can translate your object onto, and the features are absolutely orthogonal to each other. By the way, remember that the architecture of the network is no different from all the other deep networks you have been familiarized with, right? So if you choose the network you choose may not be optimal, right? The forward constructed, for example, your channel is not adequate, or the iteration of optimization may not be adequate. But keep in mind that the architecture you get is exactly the same. Then, if you have the training data, additional training data, you can always fine-tune it, use backward propagation. But the good thing here, you don't have to choose the network architecture. Also, you don't have to randomly initialize your parameters anymore, right? All the parameters are already automatically initialized by the forward construction, right? Architecture values are all constructed for you, and you see tremendous benefits by doing this. To conclude, right, today I will just talk about, right, so today, actually this relies on earlier work, right, and the principle of compression really unifies almost all tasks in machine learning, clustering and unsupervised clustering, supervised classification, and even to learn an optimal representation, right, and the deep network just arises as the strategy or algorithm to optimize the rate reduction, this objective. Give a very unified and simple interpretation of deep networks. And to compare a little bit with what the traditional neural network, this table summarizes that, right? So in the traditional, since the 1940s, when the inception of neural networks, right, the practice is always very much the same. You try to fit the input-output relationship with the architecture tried and tested, and the operators are kind of empirical. And in order to achieve invariance, you do CNN plus some augmentation, and you randomly initialize your parameters, and you train with backpropagation, you get a background. Even after you trained, right, with highly working network, it's still black box. What have learned, the representation inside is still not very clear, right? Yet the compression approach is completely the opposite, right? The objective is clear, and the network, for the first time, the network is completely forwardly computed. Right? And you can fine-tune either forward or backward way. There's nothing special about propagation once you understand deep network, the origin of it. And the whole network is a pure white box. Right? This opens up tremendous problems, right, on the theoretical front. Right? And what's the behavior of this object function, under what condition you can guarantee global optimality. And also in the case that here we talk about learned representation with the class labels given to you. What if the class is not known? Right? We don't know Z, we don't know the pi. And how can we learn those jointly? And of course, this work we only use the most naive gradient descent to construct networks. Right? There's a tremendous literature on optimization tell us how to do more efficient optimization of the rate reduction, right? They definitely gave new architectures, right? And people talk about the transformers. Turns out there's another interpretation of transformer naturally from this log-determinant rate reduction objective. Finally, of course, today we talk about a very simple vectorized or simple groups, right? Rotation translation. And the real database have additional dynamic or graphical structures and how we generalize to those cases. But now we know deep network is really trying to learn low-dimensional structures. Once we get able to get hold of those structures, we definitely be able to make neural network in the future much more robust and transferable. And also the interesting thing is that you can see that the necessary characteristic derived from this principle, right? The sparse coding, spectral computing, subspace embedding, already you see that in the nature, right? That's how human brain, right? The human visual systems has all the characteristics. If you're interested in this work, there's a list of references, right? Trace back about 15 years ago on clustering, classification, and recently we generalized this to deep networks. And also we shared most of the code examples and on GitHub and Google Colab. You can play with it. It's still very primitive, but highly promising. We are still at the early stage of developing this white box approach. So if you forget everything I said today, always remember this slogan, right? The deep convolutional neural network architectures, I'm talking about architectures, are iterative optimization schemes for compression. It's the architecture, not training neural networks. That's a different optimization problem. I'm talking about layer by layer architecture. Each layer is actually solving an optimization problem. Yeah, thank you very much. That's all.